This is another talk on the series on applied queuing system and teletraffic engineering. So my name is KT Ko or Team Ko. So I'm very happy to continue on these issues. Today's topic is on delay loss systems. And so the first question is, why do we wish to study delay loss system? So let's go to the slides. Okay, this is the motivation we have on these topics. Well, we wish to learn something about how to analyze telecom network or components of telecom networks. One good example is the router. So many ports come into a particular router with live traffic, and they exit from one particular port. So probably serve in the first come, first serve. And those who are is not served by the exiting port will be a buffer. And then when the buffer is full up, some of the packet will be dropped. So we want to know the probability of packet drop, for example. So this is important issues. And the other thing is I can think of is, how do you model call center operation? Now, in the call center, you have a finite number of holding space. So you call in, and if all the agents are busy, then you just hold it in the buffer, and then the buffer size is probably limited. So we want to know, on average, how long the customers will stay in the buffer. Okay, so those are the issues in terms of a delay loss system. So to do this delay loss system, we will look at previous topics. So I have recorded those two previous topics on early and delay system and early and loss system. So we are looking at a delay loss system. Okay, so what happened is it has a finite queue size. When the queue size becomes 0, then will be early and loss system. When the queue size is infinite, is become early and delays systems. Okay, so those I will look at the results in the previous talk and summarize it before I go into the delay loss system. And finally, the last topic is on a special case of when rho is 100% or the utilization is 100%. Now, that is some numerical problems, and we resolve this problem. So let's start off by looking at an early and loss system. So basically, it's simply, in this case, you have 5 agents, which is listen to the call, and their call arrival coming in, and they have to make an assessment whether there is an agent available. If there's an agent available, then it will go straight to the agents. Okay, if that is all 5 are occupied, then it will go to a block. It will just drop off the network. So it's the call will be blocked. And in that case, we want to know what's the blocking probability, or sometimes called time congestion. Of course, when the call is finished by the agent, the call will leave the system, and that agent become available again for new arrivals. Okay, so this is the entire idea about early and loss system. So the next one is just results. I'm just revising those results for you. Okay, one more question before I do that. Just a quick explanation on those terms. They are called candle notation. As I mentioned, this is the number of server. In this case, is 5. This is 5 plus Q, and Q is equal to 0. So that is still 5. Now the first M is the arrival process, and the inter-arrival time follow exponential distributions or a Markov. In that case, the total arrival during the interval T is what they call a Poisson process. So this is arrival process and described by the letter M, okay? The second one is the duration of the holding time, the time they talk to the agents for. And that is another exponential function. They're the same exponential function, but they are different parameters, okay? So they are different values. And the second M is the service time distribution. Okay, so with that information, we just move one more slide and look at the result. The result is quite simple, and it is called an Erlang loss formula. And this one had the E of N of A, okay? And the N is the number of server. A is the number of arrival per unit time of service time. So lambda is arrival rate. 1 over mu is the average service time. Therefore, mu is the average service rate. Okay, so that means A is a traffic intensity, is number arrival per average service time. Okay, so that describes how busy the traffic are coming in. Okay, so we have A coming into N circuit. A portion of that will be hopefully a large portion will be carried by the N circuit. Well, how many is A times the 1 minus En of A? Okay, and how many will be lost is 8 times En of A. Okay, now basically remember I told you that this formula was worked out by Erlang about more than 1917, so it's more than 100 years ago, and is on MMNNQ, okay, and but later on they found the same result can be used, but the result is insensitive to the service time distributions. So whether it's exponential distribution, whether it's a constant value, whether it's equal probability amongst a range of values, that is still good. So what happened is, what is sensitive to is the value 1 over mu, the average service time. Okay, with that information, we finished the Erlang loss system. Now the next one is Erlang delay system. Erlang delay system is basically when the buffer size is equal to infinite or very large. Okay, in that case, the we have these parameters. Okay, now because it is by default is infinite. Okay, so we assume the buffer size on here is very large. So it's basically sort of supermarket condition. You have 3 counters open for customers and people waiting in one single queue. And the waiting space could be very long, okay? Just like a supermarket. It could be a very long queue. So in this case, in this example, n equal to 3, and the buffer size is very large. Okay, for that scenario, we have this result. We have the result of the probability of delay. What's the probability of delay? If you go back to here, if you are lucky, you can walk into you can walk into the counters, and there is one available straight away. So you do not have to wait for service. So the delay time in your case is 0. And so you are not counted as a delay customer. So what is this is when all your servers are busy and you are either the first one, second one, third one in the queue, then you have to wait for service. That is a probability of delay. And the probability of delay is given by the equations of at the nth state, okay? The nth state is the nth customer occupy all the server, and the n+1 will be in the queue. So when that happens, this probability of n state multiplied by a factor 1 minus rho, where rho is the user, is the server utilization. Okay, so each server utilized on average lambda over mu, the traffic intensity divided by number of server. Okay, when rho is less than 1, this equation is valid. What happens when rho is bigger than 1? Then you have a problem of long waiting queue. That means the counters, the n number is too small to accept all the customers. Now this turned out to be in these equations, and the Erlang loss equation is here, Erlang loss formula is here, but they are there just because for numerical reasons, okay? So they make it easier to calculate because we have Erlang loss calculators and so on. And the average queue size, that is the number of person waiting at the queue, is given by this set of parameters. So dn of a, rho 1 minus rho. Okay, so that is the result of the infinite queue, and this is called Erlang delay formula. Okay. Now, the one we look at is when queue size is neither 0 as an Erlang loss case, nor infinite is Erlang delay system. It's a finite value, which is a reasonable scenario, because it's normally you have a limited number of either buffer size and so on. So basically we have the same definition, average arrival rates and exponential or pure chance interarrival time, okay? And the service rate is the service time is also exponentially distributed, and with the average duration of 1 over mu. Okay? So traffic intensity is lambda over mu. You have n server, you have q buffer. Okay, so that is our understanding of it. Okay. So next thing, we can just go back and look at this picture, which we have seen before on this picture. Now, just for argument's sake, we have a limited space. For example, we have only 4. We have only 4. Okay, so the next one come in before 4 buffer size fill up, it will just drop. Okay, and then at this stage, one customer move out, and then you have a spare capacity at the buffer. So this customer might able to go into the queue because this guy move into the first guy move into the counter. So this sort of movements basically give rise to the idea. Okay, so the idea is there are cases where the server is immediately available. You do not have to wait. There will be no waiting for you. You get service straight away. That's good. The other one is all the servers are busy and then you wait at the queue, so you are delayed. And the final one is when all the servers are busy, all the servers are busy and the queue size is not available, then you have to drop. So that is the loss. Okay, so let's look at this example with this concept. Let's look at this again. So the result I'll give you now is this. The Pn is the probability on the nth state, because the nth server is given by this relationship, where rho is the same one as we have seen. And the probability of loss is given by rho q, this. The probability delay is this. So basically, it's not a complicated set of results. So this is the result. Now I'll show you how do you use it. Okay, before I show that is a limiting case. What happens when Q equal to 0, you will assume the probability of loss in this case is given by rho Q P of n. So when Q is 0, that means it becomes P of n, which is the same definition as the Erlang loss formula. Okay. Now without Q, without any buffer or without any Q to wait, the probability of delay will be 0. Okay. And you can see that also from the equations. Rho Q and Q is 0, so that becomes entirely 0. Okay, so that is the limiting case when Q is 0. Now what happens when Q is infinite? When Q is infinite, by definition, no job or no customers will leave the system. So that loss become 0. But also you can see from the equation, when Q is infinite, these values will, rho of Q will approaching very small value is approaching 0 anyway, okay? What about delay, probability delay? If you look at this equation here, when rho Q is very small, and that will become this, which is the same definition as Erlang delay formula. So with this finished, and then we can look at the application. This is an example of applications. So what are we looking at? We're looking at the probability of loss and probability of delay. Okay, we want to know. And let's look at the case where there are 6 outgoing line. So that is a 6. And the Poisson arrival, say Poisson process, this is M. And that is the core holding time is exponential distributed. So that is another m. If you look at the q size of 2, so that is 6 plus 2. So if you look at the parameters, lambda is equal to 30. Okay. No, sorry, I'm wrong. Lambda is equal to 9. And mu is 1 over mu is 30 seconds. Or now, lambda is 9 core per minute. Okay, so you have to change that into minutes, which is about half minutes. Okay, so that is minutes. Okay, so we have 9 core per minute. And so what do you have now is A equal to 4.5. And therefore rho divided by 6 is equal to 0.75. Okay, so basically we have all the parameters, and all you have to do is work out the P6 values, and you turn out to be about this 0.1282, and the probability of loss is about 7%. Okay, so just utilize the last results I showed you before. Now, we look at an interesting case. When Q equal to 0, what happened to the P loss? P loss should be equal to P6. And P6 is equal to early loss E6 4.5. And that is about 15%. Now, what I can say is by adding two buffer, you are basically change the loss rate from 15% to 7%. Okay, so the buffer is utilized quite effectively and reduce the loss rate by half. Look at the case of P delay, which is similar to the result I show you. So you find P6, and then you have this simple term. You turn out to be a 20.2244. So in fact, one fifth of all the arrival will be delayed, and about 7% will be dropped. Okay. What about when Q is infinite? What happens is that is give you about 42% of delay. That means all the jobs are holding in the infinite buffer, in the infinite queue, and they are so the server keep busy, and therefore more people are waiting. Okay, so this is the application, and that's the way you could possibly see those concepts. Okay, let's look at the theory. It's not very hard. The theory starts off with a Markov chain. For those who have seen my Erlang loss formula and Erlang delay formula lecture, those issues familiar. So you start off with the idea of state. A state is number of customer being in the system, and when it's in the end state, is occupy the server. When n+1 t is the first one in the queue, and this is the last one in the queue. And what happened to the next one? That will be dropped, lost. Okay, so those are n+1 to n+q. They are waiting for service, so they are delay items, delay state. And the Markov chain is one transitioner down, and you can see the arrival rate is constant, and the departure rate is n mu, 3 mu, 2 mu is state dependent. Now, as I explained to you before, the concept of state in this case, you have, if a counter in a supermarket can serve 12 customers per hour, that is one counter. if you have two counters on average, they work together and they can service 24 customers per hour. Okay, so that is mu, 2 mu, and if a third counter open, there's 3 mu. So it's up to the n mu, that is the last server. And then the next one, because it's all the servers are busy, and there's still n mu. Here is not a server, is in the queue. Okay, so that is in the queue. So the service rate at this stage is n mu. So that is basically the idea here. So we have a recursive formula. So the recursive formula is simply this. So for example, mu2 p2 is equal to lambda of 2 mu p1, and p1 can be written as lambda over mu p0. So this can be written as lambda 2 mu lambda mu p0. Basically, you can express any state in terms of p0. So there are two sets. One is before n, one is after n. After n, the all are n mu. Okay. So with that concept, we can go to the next slide. The next slide is then the PI have two possible sets. One is before n. Okay, one is before n. Just clear that, before n, and that is p0 a to the power I factorial. And the other one is the I minus n component. Okay, so that is basically the number of term between n plus 1 up to n plus q. Okay, so it's n plus 1. Okay. So from normalize this term, we add those together, they should be equal to 1, and p0 should be this term. Okay. So that is a minus 1 term, so it's 1 over, so it's equivalent to 1 on top. This is on the numerator. Okay, so here this term is basically is equal to rho plus rho's square plus rho 3 up to rho q. Now, basically you have the infinite series rho 1 plus, if you know the infinite series of I equal to 0 to infinite, and rho I, that is equal to 1 minus rho. And with that, you can calculate from here to here, because in this term, you have that term minus 1, because that one term is not appeared here. And all this, and then minus all the term which is from rho q to power, rho to the q plus 1 power, and so on. Okay, so they turn out to be, if you do the summation diligently, and then you should have this expression. Okay, so with that, so we get the p0, and so we have this term, and don't forget that n factorial cancel out with that n factorial. That is on the bottom. So what you have is this term. So you have this term here. So you have this term, the Erlang loss formula term, and that as a numerator. Okay. So Pn is 1 over all these expressions. And then the probability delay is basically a Pn when it's in state n. So you are the first one waiting. And this, when it's in state n plus q minus 1, when your rival found this state, it will be the last one waiting in the queue. Okay, so that is 0 to q minus 1. And they turn out to be this expression. Okay, so that expression is simply 1 plus rho square plus rho q minus 1. So using the infinite series we have previously, you should be able to get this expression. Okay, interesting enough, now if Q is very large, and that term, this term disappear. Okay, so that is basically 1 over 1 minus rho. Okay, now on the other hand, if Q is 0, that means there are no job waiting in the buffer. Therefore, every job either gets service or drop or loss. So there are no delay. What about loss probability? Loss probability is when all the jobs are in the when in the state n plus q, and that is given by these expressions. Again, if you look at when q become infinite, very large, that p loss become 0. When q is 0, that p loss will becomes Pn or Erlang loss formula. And the next thing we want is the average Q size. So the average Q size is given by this term. So either is 0 plus 1 rho 1 2 rho 2 plus up to Q rho Q. Now, basically, that is a closed form solution. It's called arithmetic and geometrical series. Okay, you can find that out. And so, in fact, it's a closed form. That's probably useful when Q is very large. When Q is small, just do this summation. You know, if Q is small, then this term can be easily calculable. Okay, so the average Q length. Now, as I told you, you only wait in the queue because the server are busy and there is a waiting space in the queue. If there's no waiting space in the queue, your call will be dropped. Your service, they won't accept you waiting. So that is a loss. So if I know, oh, there's one thing, oh, just remind you of the relationship between arrival and numbers is given by the little formula, which is simply this, and the numbers of jobs is equal to average arrival rate multiplied by the waiting time. Okay, so if I know the n values, okay, I can work out the w values. Okay, in the case of here, we want to work all except a call in the server and in the queue. So that is 1 minus the probability of loss. So lambda times 1 minus probability of loss, that is the call, which is, or the customer which go into the queue, either in the queue or in the server straight away. So in that case, we know NQ, and then we can divide by this. Okay, so this 1 minus N, P loss is here, is 1 minus N plus Q, which is this value here. Okay, so we are looking at the acceptor core. The other thing we are looking at is probably the more important part is what happens when core are delayed, because what's the waiting time for those who have to wait in the queue? So the cores are in queue. So in this case, the is lambda q, so nq divided by arrival at the queue. So it's lambda time probability of delay. Okay, so probability of delay is given by this relationship. Okay, so with that, then we could finish the talk about finite queue, multiple server system. Now, there is certain parameters happen when rho is equal to 1. If you notice the there are terms, for example, PM is one the denominator is 1 minus rho. Okay, so 1 minus rho, if rho equal to 1, that become very large. Okay, so with that calculation of Pn, and also the calculation of delay time, okay. Calculation of delay time. So that is 1 minus rho there. So rho equal to 1 gives some problem. So to resolve this problem, we have to go back and look at the definition in the idea, okay? So resolve those problems of 1 over 1 minus rho. Now, when rho equal to 1, which is possible, that means the lambda over mu equal to A. Now, is that possible? Can rho be equal to 1 and bigger than 1? If rho is bigger than 1 or equal to 1, what happens? The loss probability probably high. The system is still possible. I can imagine if you have A large, then what will happen is the queue is always full, the server is always busy, and the loss is high, okay? But how do you work this out? Work this out by looking at from the first principle, okay? If you look at from first principle, rho equal to 1, that means the summation, the Pn, let's go back to here. Let's go back to this definition, this summation, that Pn is given by the this term here, all right? This term, okay? So what happens is when rho equal to 1, this term will become 1 plus 1 plus 1 up to the cube term. So that basically is this idea here. That is this idea here. Okay, so altogether you have Q. That is the definition of P0. Okay, the normalizing that values. So Pn can be derived, and the idea once you know P0, so you know then you have the Pn, okay, and that is equal to this term. So that is also equal to P loss. What about P delay? If you look at definition of P delay, it basically say P of n plus P of n plus 1 plus up to P of q when the arrival found that in this state, okay? So if that rho, that is rho to the power j, if rho is equal to 1, that is 1 to the power j, and that should be QPN. All right, so that is the resolve a special case of when the rho is equal to 1. Okay. Now the final concluding remark. So what did we learn? We learned the multiple server finite queue, which is the MNNN plus Q case. Okay. Now in this case, we just, so what we have where Q is as 0, it's not 0, it's not infinite, but the finite values. So what do we find out? We find out probability delay, probability of loss, and then the average size in the queue, the waiting time in the queue. Okay, so what we can also look at the case where the when you know WQ, then you have the waiting at the system, and that is equal to WQ plus 1 over mu, okay, the average service time. And once you know WSys, then you can work out the number in the system is lambda times WSys. Okay, so there are two limiting cases, Q equal to 0. In that case, P loss is equal to En of A, which is the same as the early loss Q, okay, early loss system. And P delay is equal to 0 because there's no waiting, no queue for you to wait. So all the delay, there's no delay. Same when there's infinite queue, there is no loss because every job is kept in the queue. And the probability delay is equal to Erlang delay formula. Okay, so it's the same as MNNQ. And we also resolve the numerical issue when rho equal to 1. With that, we finished the talk. So I hope you found it interesting. Okay, so bye-bye.